Hi, my name is Riya Kumari and I go to the University of Maryland. My mentors are Varun Kazireddy, Yayu Hu, and Sebastian Scherer from the Air Lab at Carnegie Mellon. This summer, I worked on improving depth completion for aerial inspections. The motivation behind this project is to use UAVs for doing infrastructure inspections. However, to be able to detect defects like concrete spalls, one needs to have very precise depth measurements. Accordingly, depth sensors like LiDARs are used. However, they measure depth in a very sparse manner, where only a few pixels of an image will contain depth values with the rest empty. To infer the missing depth values, we can use visual details from camera images. Our goal for the summer was to fuse the information from a camera and sparse LiDAR to achieve highly precise, dense depth. This is also known as the task of depth completion. Here is an overview of the approach we take. We employ a deep learning-based approach. For our data, we choose to focus on a specific kind of infrastructure defect called spalls. This is a type of defect where areas of concrete have cracked, crumbled, or chipped. Our goal is to have precise depth in this kind of defect region to be able to detect it accurately. We fine-tune a state-of-the-art depth completion model, completion former, on concrete spall data using NYUV2 pre-trained weights. And we address class imbalance by modifying the loss function. The data we start off with is in the form of 3D point clouds. The real spalls are at the bottom and are shown in black. They do contain texture, however, it is hard to visualize. The simulated spalls do not contain any textures, but they are annotated in terms of which points are part of defect regions and which are not. We apply textures to the simulated point clouds with a difference in intensities between the defect and non-defect regions. We then define a virtual camera and place it close to the point clouds and transform the 3D points to 2D using the z-depth to create a depth map. In the end, we have an RGB image with corresponding ground truth, depth, and annotated defects. Before we start fine-tuning, we conduct a sparsity study where we need to understand how many sparse depth points we actually need to detect spalling. We first use completion former with our real spalls data to do a simple sparsity study. We are trying to see the behavior of the model as we change the proportion of depth points given as input. Passing higher proportion of depth points doesn't do very well. We try to find the model's sweet point, and that is 10%, so we use that to fine-tune. When we are doing depth completion in the real world, one key point to consider is the issue of class imbalance where the distribution of data is uneven. For our case, the distribution of depth points sampled in an image is not uniform. This means that more depth points are sampled in non-defect regions, and the model can become biased towards accurately predicting the good regions while ignoring the ones with defects, which is what we are interested in. In a given image, a defect region makes up less than half of the image, and with already sparse depth, we have less information to infer the missing depth. To account for this, we modify the loss function to give more weight to predictions in defect regions. The loss can be read as for every depth pixel that is not zero, compute a combined L1 and L2 loss of the depth prediction and ground truth. An additional term that we add is to compute L1 loss only for the defect regions and weigh that 2 times. Our fine-tuned model shows improvement over the baseline. We lower RMSE and MAE numbers, and it can be seen in the error maps that there is a significant improvement in both defect regions and non-defect regions. Future work would involve enhancing depth completion to work with an even smaller number of depth samples by exploring the possibility of learning the geometry of defect areas from the RGB images. Finally, I would like to acknowledge all the institutions and labs that made this project possible and give special thanks to Rachel Burson and Dr. John Dolan for their support throughout this program.